In the previous sessions, we have looked at what are matrices and we have seen different types of matrices. Now let's look at algebra of matrices. So first of all, let's look at equality of matrices. So we have a matrix A, a 2 by 2 matrix, and another matrix B, which is again a 2 by 2 matrix. Now A is equal to B only if A11 is equal to B11, A12 is equal to B12, A21 is equal to B21, and A22 is equal to B22. Of course, if we have to do this element by element comparison, then the order of A and the order of B should be same. So in general, for two matrices C and D of order m by n, C is equal to D if and only if C sub ij is equal to D sub ij for all I and j. And as I mentioned previously, in particular, two matrices can be equal if they have the same order. Now let's look at addition of matrices. So we already have A and B. So when we add A and B matrices, we will get another matrix C. So matrix A plus matrix B. The result would be a matrix containing elements which are the sums of the corresponding elements in these two matrices. So A11 plus B11, A12 plus B12, A21 plus B21, and A22 plus B2. So here again, two matrices can be added only if they have the same order. In general, two matrices C and D of the same order gives us another matrix of the same order, and each element of the resulting matrix E sub ij is equal to Cij plus Dij, where I is between 1 and m and j is between 1 and n. For every matrix A, there exists a matrix minus A such that A plus minus A is equal to O, that is a zero matrix. So here, this is matrix A, and negative A basically means each element of the matrix is negative. So A11 plus minus A11 gives 0. And similarly, the rest of the elements. So we end up with a 0 matrix. Now subtraction of matrices. Pretty straightforward. A is equal to the matrix. We have B equal to this. And A minus B will again give us a matrix. So A11 minus B11. A12 minus B12. A21 minus B21. A22 minus B22. So in general, Cij is equal to Aij minus Bij, where I is from 1 to m and j is from 1 to n. Two matrices can be subtracted only if they have the same order. So we have seen equality of matrices, addition of matrices, subtraction of matrices. Now, a scalar multiplication of matrices. So we have A. Let K be a real number. Then C is equal to K times A. So C is equal to K times the matrix A. Here, the way the multiplication works is that each element is multiplied by K. So Cij is equal to K times Aij, where I goes from 1 to 2 in this specific case, and j goes from 1 to 2. Scalar multiplication satisfies the following properties. Distributive property over matrix addition. So we have a scalar K times A plus B is equal to K times A plus K times B. This is distributive property over scalar addition. So we have K plus L times the matrix A is equal to K times A plus L times A. Associative property. K times L times A is equal to K times L times A. Finally, the identity. 1 times A is equal to A. Now, these are the properties with respect to scalar multiplication. Transpose of a matrix. So, given a matrix A, its transpose is obtained by interchanging rows and columns. That is A to the power of T, or rather we should read it as A transpose is equal to the matrix whose elements are A sub Ji. So do you notice what is happening? Here the subscript is Ij. Here it becomes Ji. So rows are becoming columns, columns are becoming rows. In the previous session, we have seen this with respect to symmetric matrix and skew symmetric matrix. So A is equal to A11, A12, A21, A2. So the transpose of that will be A11 and A22. That is the elements, the principal diagonal remains the same, but these two change positions. So think of it like this. This A11, A12, the first row has become the first column. Second row has become the second column. Let's take another example, a 2 by 3 matrix. So its transpose would be the rows become columns. So we end up with 3 by 2 matrix. If we take a transpose of a transpose, we get back the original matrix. So repeated transposition alternates between A and A transpose. An odd number of transpositions gives us A transpose, while an even number gives the original A matrix. Two successive transpositions cancel each other. And with respect to the identity, I transpose is equal to I. A equal to B implies that the transpose of A will also be equal to transpose of B. And transpose of the sum and difference of two matrices will be equal to the sum and difference of the transpose of the individual matrices. So that is algebra of matrices. With respect to equality, addition, subtraction, scalar multiplication, and transpose of a matrix. I think that is it for now. Let's meet in the next session.